name of the topic. So our subtopic in this topic is solubility. That is the first subtopic. The second subtopic is solubility product, and the third subtopic is ionic product. So let us now remind ourselves from what you studied, since it is a revision about the word solubility. Solubility normally refers to the maximum mass in grams or number of moles that can dissolve in a gram in a given mass of a solvent, but at a given temperature and the pressure. Now, the maximum mass dissolved into a solvent at a given temperature results into a solution known as saturated solution. So we have saturated solution. So which means that you can define it as a solution which cannot dissolve more solute at a given temperature. So this is what we call it, saturated solution. Now let us consider that if we have a solvent, you have a solvent and you dissolve the spangly soluble solute inside that solvent. It will reach a point whereby the solvent will not be able to dissolve more solute. And when the solute added in excess, then it will result into formation of a solute where will settle at the bottom of the solution. So when the excess solute is added, and when the excess solute is added, the solute will settle on the mixture and resulting into a formation of an equilibrium known as dynamic equilibrium between the solid substance and the solution substance. So here, if we have the solid substance, we will establish an equilibrium which is dynamic equilibrium with the solution substance. As what you have said, that equilibrium is known as dynamic equilibrium. Now let us consider our spangly soluble substance. Consider our spangly soluble substance, which let's say is AX and BY, which undergoes dissolution into a solvent. So we have AX, BY, which is our solid now, that establishes an equilibrium with the solution, resulting into formation of, here will be A power Y, which is now positive, but if you balance here must be X, and B, that will be a cation, an anion with a negative X. But once balanced, there must be Y. This is an aqueous. So this is our equilibrium which is being now established in our spangly soluble substance, which is AXBY. Now, during the solution now, if we go back to the law of mass action, here, since this is an equilibrium constant, then an equilibrium constant is established since it is an equilibrium reaction. So our equilibrium reaction, which is now Kc, will be equal to the concentration of the product, then it divided by the concentration of the reactant according to the law of mass action. So here you'll be having A, which is an aqueous but raised, equals to their stoichiometric coefficients. You remember the law of mass action. So here X is our coefficient, which will be now there X, then will be times the concentration of B, which is our ions, but this concentration of B, the stoichiometric coefficients of B is Y, so raised to power Y. Now this is an aqueous and this is also an aqueous. Then divide by the concentration of the reactant, which is our solid substance, which is AX, BY, which is solid. Now that is our equilibrium reaction that will be established. From there now, multiply by the concentration of the solid on both sides. If we multiply there, you'll have now Kc will be times the concentration of AX, then BY, which is our solid substance which undergo dissolution, will be equal to concentration of A, Y positive, then raised to power X, then times concentration of B, X, then raised to power Y. Since the concentration of our substance, which is now solid, this one is negligible or is very, very small, so that's why we neglect it. Then the expression, the Kc times the concentration of A, X, B, Y, gives us another constant which is known as solubility product. So this is equal to what we call it solubility product, or in the other way we also call it as solubility constant, and it is denoted by KSP. So KSP stands for the solubility constant of spangly soluble substance. So that is now our new constant. From there now, from that equation, it means that the KSP of our equation now, that is KSP, will be equal to the concentration of A raised to power Y, then to raised to power X times concentration of B negative X raised to power Y. So that is our solubility constant or product. So how can we define it? You can just define it as the product of the concentration, the product of the concentration of the ions which are being obtained after the dissolution of the spangly soluble substance, but it must be at a constant temperature and pressure. So which means that the KSP as our equilibrium constant also can be affected by temperature. So that is now how do we obtain what we call it KSP, or solubility product or solubility constant. Now we have different factors that affect the solubility constant or solubility of a substance. So in our discussion for today, we'll only consider two main factors. And these factors are, we'll consider about the common common ion effect, and the complex compound formation. So this is our main part to consider on this discussion. We'll consider the only two factors, which is the common ion effect and the complex compound formation. How do they affect the solubility of a substance, or how do they affect the solubility constant of a given reaction? Now, if we consider the common ion effect, common ion effect. Common ion effect is an effect which decreases the solubility of a substance when that strongly soluble substance is added into a solvent containing one of its ion. That is what we call it common ion effect. So an effect which is now decreases the solubility of that substance in that solvent is known as common ion effect. Let us consider if we have, let's say, our solvent, which is lead nitrate. If lead nitrate is our solvent, and into this solvent we add lead chloride, as our solute. Now our ions which are present inside the solvent is lead and nitrate. So here we have our ions which is lead and the nitrate ions. We have lead and the nitrate ions. So what our solute is being added into it is contain the ions which is lead and the chloride. So here this one contain lead and the chloride. So do you see now what is common here? The ions which are common is lead. So the solubility of lead chloride into lead nitrate will be decreased due to the presence of ions which is now inside the lead nitrate, and that common ions is lead. From there now the solubility of lead will be decreased in lead nitrate than if you dissolve it into a pure water which does not contain any of its ions. So the effect which is now taking place there is known as common ion effect. And here, according to Ricartesian principle, the solubility now product will also be affected due to the principle which is known as the Ricartesian principle. I know you remember it, and you can state it that the effect always will change in order to counteract the effect that have been produced by that solution. So this is what we call it common ion effect. And we have some of the examples that we will consider later on after our discussion. Another factor is the formation of complex compound. Normally a complex compound is a compound which is made up of central metal atom and the ligands. So most of the ions, when added into a solution containing the ions, and those ions that are being added are added in excess, there is a tendency of formation of a complex compound which becomes soluble. For example, if we have, let's say, silver nitrate. Taking an example of, you have a solution of silver, and that solution which contains silver ions, you add chloride ions, then it will result into formation of a white PPT of silver chloride. That is under normal condition, and this is solid. But in case if chloride ions are in excess, you add excess chloride ions, will combine with silver and form a complex compound which will be of silver, of dichloro silver 1 ions. And this now is an aqueous. So this is now soluble. So the solubility of silver have been increased after increasing the concentration of chloride ions. That leads into formation of complex compound, which is our soluble compound. From there now, let us now go to some examples and see how can you use them in calculating the solubility and the solubility product, and to see how common ion effect can affect the solubility and solubility constant of the Spangly soluble salt. So after a short break, we'll be back for that continuation. Welcome back now to solving some of questions that we need now to consider in this subtopic that you have discussed. And the first question is that what would be the KSP in moles per decimeter cubic of a saturated solution of calcium fluoride, which is this one, containing 0.0156 gram in a liter of solution. So you have been asked to calculate the KSP, which is our solubility product or solubility constant, and our Spangly soluble substance is calcium fluoride. So the first thing to consider is that you have to write the dissolution reaction equation of calcium fluoride. So here for question 1 now, our Spangly soluble salt is calcium fluoride. And normally calcium fluoride undergo dissolution to release calcium ions and the fluoride ions, which after balancing here you put 2. From there now, you remember how do we determine the KSP? We said that KSP is the product of the concentration of the ions of that Spangly soluble substance. So here, since we have calcium and the fluorine, so let X be or stands for solubility of calcium fluoride. So since calcium fluoride dissociate or undergo dissolution to release 1 mole of calcium ions and 2 moles of fluoride ions, so our solubility for calcium fluoride is X. So if it undergo dissolution to release 1 mole of calcium ions, that means this one will be also X. And here this one will be also 2X, since it undergoes 2 times than the concentration of calcium fluoride. So if we go back to the KSP expression for our equation, KSP is equal to the product of the concentration now will be of our ions, which is calcium ions, then will be times the concentration of fluoride ions. But remember the solubility product, states that it must be raised to the power equal to their stoichiometric coefficient. And the stoichiometric coefficient for calcium ions is 1. But for fluoride ions is 2. So here must be 2 there. So since KSP for this square bracket stands for concentration in moles per decimeter cubic. So here for our KSP now here will be equal to the concentration of calcium ions, which is now X. Then times the concentration of fluoride ions, which is 2X. But 2X, then we have square. Now, from there, if we go back to our question, the data given from our question, data given, we have the molar concentration in gram per liter of calcium fluoride. And we have said that the concentration to be expressed here must be in moles per decimeter cubic. So the calcium fluoride containing 0.0156 gram in a liter of solution at that temperature. So the concentration or molarity is being obtained by taking the concentration in gram per decimeter cubic over molar mass. And the molar mass of what here? Of calcium fluoride. Now let us find the molar mass of calcium fluoride. The molar mass of calcium fluoride, this is calcium fluoride. We have been given the mass of calcium, which is 40. Then will be plus the molar mass of fluorine, which is given there is 19. But 19 times how much? Times 2. And if you use your calculator here, you'll get 40. Then 19 times 2 is 38. Now adding, you get 78. This is the molar mass now of calcium fluoride. Now if we substitute to the equation here, the concentration in gram per decimeter cubic we have been given, which is equal to 0.0156. This is gram per decimeter cubic. Then you divide by molar mass, which is 78 gram per mole. Then grams will cancel with grams, so you will remain with the units of moles per decimeter cubic. Now, my dear students, you can now take your calculator and calculate what will be the molarity or concentration in moles per decimeter cubic of calcium fluoride. So taking 0.0156, then divided by 78. The answer is 2.0 times 10 power negative 4. So the answer here is 2.0. The answer is 2.0. 2.0 times 10 power negative 4. And this one now, the units is moles per decimeter cubic. So that is the molar, the concentration of calcium fluoride in moles per decimeter cubic. Now, since we have said that here, the KSP, from now, KSP, which is equal to concentration of calcium ions times concentration of fluoride ions, then square. But our solubility here, which is X now, is 2 times 10 power negative 4. So the KSP now will be equal to X, which is 2.0 times 10 power negative 4. Then it will be times 2 times 2.0 times 10 power negative 4. Then this will be square. From there now, my dear students, you can now take your calculator and use it to calculate the value. Here will be 2.0 times 2, then exponent 2.0 times 2, exponent power negative 4, then 2 times 2 equal to 4, exponent negative 4, 2 times 2 exponent negative 4, then this one now square, then the answer is 1.6 times 10 power negative 7, then times 2.0 exponent negative 4 also. The answer is equal to 3 times 2 times, the answer is 3.2 times 10 power negative 11. Now the question here is, what will be now the SI unit of our KSP? The SI unit of our KSP will be obtained from the KSP expression. And the KSP expression, this one, which means that here our concentration for calcium is in moles per decimeter cubic, and the concentration of fluoride ions is also in moles per decimeter cubic, but this one is square. So if this one is square, then here that means is raised to power 1. So if you take this one times this one, but this one will be 1 plus 2, which will give up 3. So here it's the same to take moles per decimeter cubic, then raised to power 3. That will give up moles 3, then decimeter power negative 9 decimeter cubic. So that will be the SI unit of our KSP will be moles cube, then power negative 9 decimeter cubic. So this will be the KSP value of calcium fluoride, which we have been now asked to calculate it. So that is now about the first question, which employ you to calculate the KSP value of the given Spangly soluble salt. So let us now go and consider the second question. Okay, now let us consider question number 2. Question number 2 is that what would be the solubility of silver chromate in 0.035 moles silver nitrate if the solubility product of silver chromate is 1.08 times 10 power negative 10 moles square per decimeter cubic raised to power negative 6. And given the relative atomic mass of silver is 108, that of nitrogen is 14, and that of oxygen is 16, and that of chromium is 52. So that is our question now. If you compare this question to our knowledge that we have discussed, it is concerned about the effect of common ion or common ion effect. How does it affect the solubility of a substance? So that is the question now, how does it concern? So let us now start solving that. We have been given the concentration of silver nitrate. So the data given now, question number 2. Data given, we have the concentration of silver nitrate, which is 0.035. This is moles per decimeter cubic. And we also have been given the solubility product of silver, which is now the KSP of silver chromate, which is equal to 1.08 times 10 power negative 10 more square decimeter per negative 6. So that is the data we have, but you have the relative atomic mass of these elements. Now, we are now asked that what will be now the solubility. We are calculating the solubility of silver chromate. In what? In silver nitrate. So first point to consider here, you have to write the dissolution reaction of silver chromate. So silver chromate, which is our Spangly soluble salt, this one dissociate to release silver ions. To balance here must be 2 aqueous, then will be plus chromate, which have -2 there, -2, this value here. And now to balance, it is balanced. Here we have 2 and there we have 2. So the KSP now of this reaction equation given is this one. So we have first to find the solubility of silver before the addition of that substance. So here the solubility of silver, which is now KSP now, is being obtained by taking the concentration of silver will be square, then will be times the concentration of chromate, and let the solubility of silver be X. So if we let the solubility of silver to be X, then here KSP will be equal to X, then square will be times X, which will be the solubility of chromate ions. So here the KSP now will be equal to X cubed. So to find X will be equal to cube root of KSP. And if we substitute now our data, we have the KSP given there, then the X will be equal to, KSP is 1.08 times 10 power negative 10 more per, you can write the units, and this is an under root. So, but this is cube root, not under root. Since it is 3 there, so here must be 3. So here, if we find now the cube root of 1.08 times 10 power negative 10, using now your calculator, that is 1.08 exponent negative 10, then its answer is 4.76 approximately, then times 10 power negative 4. So this will be moles per decimeter cubic. So that is the normal solubility of silver chromate. So let us now find how would this solubility be affected by common ion effect when it dissolves now in silver nitrate. So our next now procedure is to write the dissolution reaction of silver nitrate. Silver nitrate undergoes dissolution to release silver ions, then plus nitrate ions. So what silver nitrate will be adding to the solubility of silver chromate remember silver chromate here is this one. Undergoes dissolution to release silver ions, then plus nitrate plus chromate. Aqueous. Now remember we said that if we rate the solubility of now for silver in this one, let us call it as Y. So here will be 2Y and here will be what? Y. If we rate now the solubility of silver nitrate, silver chromate in silver nitrate. But silver here releases also here the concentration of silver. We have been told that it is 0. If we go to the question, we have been told that it is 0.035 more. So here is 0.035 more. So this is the common ion. That therefore here this will be adding 0.035 to the concentration of silver ions. Now, if we now go and consider the KSP of silver chromate will be equal to 2Y, then it will be plus 0.035, then times the solubility of chromate ions. Now, if you remember that this one must be squared due to presence of 2. But 2Y plus 0.035 is approximately equal to 0.035. Why? This is due to the smallest value of Y. So when multiplied by 2 then plus 0.035, it doesn't affect the constant. So it remains to be 0.035. So if we now consider our KSP will be equal to 0.035 will be square, then it will be times Y. We are looking for solubility, which is Y now. And the KSP, we have the KSP. So Y here will be equal to KSP, then divided by 0.035, but this is square. Now use your calculator now to find it. Since the KSP, we have it. We have the KSP, which is, so here, Y will be equal to KSP, which is 1.08 times 10 power negative 10, then divided by 0.035 square. So take it now and feed it into your calculator. 1.08 exponent negative 10, then divided by 0.035 square. Then the answer is 80.8. So we get the answer Y, which is equal to 80.8 to approximately then times 10 power negative 80. This will be moles per decimeter cubic. So this is now the solubility of silver chromate in silver nitrate. So let us now compare the solubility of silver chromate in water and in silver nitrate. In water we have obtained, which is, we have said that it is 4.76 times 10 power negative 4 moles per decimeter cube. But here we have got 80.82 times 10 power negative 8. So you can compare yourself, my dear students, which one is lower than the other. So this one is lower than this one. If we compare now the solubility of silver chromate in water And in silver nitrate, which means that in common ion effect, this one is lower than that one. So the common ion effect have decreased the solubility of silver chromate from this one to this one. So that is what we call it common ion effect. So the ions present in the solution decreases the solubility of that substance that contain ions that are present in that solution. So that is now how you were supposed to go about that second question. Now from there, let us go and consider the third question. Okay, now let us consider the third question. And the third question employ you to use the knowledge of complex compound formation. Since you remember that we have discussed here that one of the factors that affect the solubility of a substance, a strongly soluble substance, is the formation of complex compound. So here the question is that A, why the solubility of silver chloride in water decreases upon an addition of dilute hydrochloric acid, but increases when concentrated hydrochloric acid is added. So this is chemistry, so you have to show it and verify it by using equations. So here that it is the solubility of silver chloride in water decreases upon addition of dilute hydrochloric acid. What is happening here that if it's silver chloride, then you add dilute hydrochloric acid, it will end up leading into formation of precipitate of silver chloride, which is solid. That is what is being happening, solubility of silver chloride in water. So it leads into formation of PPT, which is silver chloride. But when concentrated hydrochloric acid is added, that means now here you have silver ions, which is now an aqua. If we write it, these are ions which are present. Now you are adding the concentrated hydrochloric acid. Concentrated hydrochloric acid releases chloride ions that will be reacting with the silver ions. So here will lead into formation. This is now in excess. This will lead into formation of a complex compound of silver, of dichloro silver argentate 1 silver. So this is an aqueous. So that is now will be the product, and this complex is is soluble. So that's why now we say the solubility of silver chloride in water decreases on the addition of dilute hydrochloric acid, since there are few number of moles of chloride ions that will be reacting with the silver ions. But when it is concentrated, then the chloride ions will be in excess. That will lead into formation of a complex compound, which is dichloroargentate 1 ion, which is soluble. So that is about the first question. Now if we consider the second part of the third question, that lead chloride is sparingly soluble in pure water but soluble in concentrated hydrochloric acid. This is the same to what we have discussed above there. But here, instead of being silver chloride, it is lead chloride. In concentrated hydrochloric acid, that means there are more chloride ions that will react with lead and lead into formation of a complex compound of lead. So here, that means if this is lead ions, will react with chloride ions, which is in excess. Chloride ions are now in excess, and they lead into formation of a complex compound of lead. Which is now an aqueous. So it is now lead into formation of tetrachloroprombate 2 ions, which is now our complex compound, which is soluble. This is happening when it is in a concentrated hydrochloric acid. So the solubility of lead chloride is being increased. So lead is soluble in that solution, but not soluble in pure water. And the third part of our question is that copper 2 hydroxide dissolves spangly in pure water, but it dissolves readily in presence of concentrated ammonia solution. So what does it mean here is that copper hydroxide is this one. Copper hydroxide, this is copper hydroxide. This is copper hydroxide. It is spangly soluble in water, in pure water, but in concentrated ammonia solution dissolves readily. Okay, now is that we have now copper 2 ions from copper hydroxide. This one now is an aqueous. So in concentrated ammonia solution, that means we have now ammonia solution, which is an aqueous. So what will happen? The ammonia, which is our ligands now, will combine with the copper 2 ions and leading into formation of complex compound of, which is now will be the tetraamine, copper 2 ions as an aqueous. So here the complex compound formed here is soluble. So that's why we say now the copper hydroxide is spangly soluble in water, but in presence of concentrated ammonium solution, which is ammonium hydroxide, the ligands now, which is amine, will combine with copper 2 ions and leading into formation of a complex compound, which is a soluble compound. So that is now what it was supposed to be for the third part of the question. Another question will be now your assignment to do it. So I will read it to you and copy it, then do it as your an assignment. Now the question number 4 is now your assignment. How many grams of silver chloride will precipitate if 5.8 gram of 0.1 more sodium chloride solution is added into the saturated solution of silver chloride, given the KSP of silver chloride is 1.6, 9 times 10 power negative 10 mole square, given also the molar mass of silver and the molar mass of chlorine as well as the molar mass of sodium. So this is now your assignment. You can now try. It is about the common ion effect. From there now, we have seen how you can determine the solubility and the solubility constant of a given spangly soluble salt, and how these factors, which is the common ion effect and the formation of complex compound, affect the solubility of this spangly soluble substance. So this is now the end of our discussion for today. Then the next lesson we'll discuss on another subtopic, which will be now the ionic product, which is another subtopic of our topic. I'm sure you have enjoyed our discussion. Thank you very much, and thank you for listening. So see you next period.
Kipindi cha Darasa Online kimeletwa kwenu na Chuo Kikuu cha Sauti Mbeya. Uongozi wa Chuo Kikuu cha Mtakatifu Agustino Tanzania, Tawi la Mbeya, unapenda kuwakaribisha wahitimu wote wenye sifa za kujiunga katika kozi mbalimbali zitolewazo na chuo kwa mwaka wa masomo 2020-2021. Chuo kinatoa kozi ya shahada ya juu ya elimu, yani Postgraduate Diploma in Education, shahada ya kozi ya elimu, yani Bachelor of Arts with Education, shahada ya utawala wa biashara, Bachelor of Business Administration, na katika michepuo ya rasilimali watu, Human Resource, ugavi na manunuzi, Procurement and Supply Chain Management, usimamizi wa masoko, Marketing Management, uhasibu na